All right, we're given two events, probability of A, which is 0.6, probability of B is 0.5, and their union, which is 0.8. And we're asked, are they independent? Are they mutually exclusive? So let's answer the mutually exclusive part first. It's a little bit quicker to answer. So for two events to be mutually exclusive, it literally just means that they can't occur at the same time. So in a Venn diagram, it would look something like this. So this is event A, this is event B. See, there's no overlap. This has to be the case with any mutually exclusive, any two or more mutually exclusive events. They cannot overlap. So let's check if we can possibly fit A and B to a Venn diagram such that they don't overlap. So A is 0.6, so it's going to take up a huge space in here. 0.6 is very likely. Then 0.5. Let me ask, is there enough room to put 0.5 in here such that it won't overlap with this? I mean, you can try, but anything that's not in here is just 0.4, which is less than 0.5. But yeah, you have to put A somewhere overlapping into B. So therefore, they can't be mutually exclusive. You can also think of it this way, like 0.6 plus 0.5 is greater than 1. So therefore, that's more than the outcome space. They have to have some overlap. So the answer to this question is that they are not mutually exclusive. No, not, then chalk. Not mutually exclusive. All right, so now we're asking, are they independent? This is a much trickier question. So the definition of independence is that A given B has to equal to probability of A, simply, without knowing B. So we're asking if these are equal. We know what probability of A is already. It's 0.6, it's already given. 0.6. And now we're going to ask A given B. So the formula for A given B is A intersect B over the probability of B. And let me show you why this is true, because it's not at all obvious why this is equal to this. So I'll do that over here. So you have an outcome space. You have events A and B. And you want to know what A given B is. So when we do A given B in a Venn diagram, we're just literally going to reduce our outcome space, what we're looking at, to just event B. And then we're going to see what the probability of A is. So to reduce our outcome space, we're basically looking just at B. So that's why we're dividing by B here. Because instead of dividing by the 1, we reduce it to B, the probability of B. And then what's left of A in here is just this part right here, what we need probability of A given B. The only A left in here is this part, which is just simply A intersect B. All right, so hopefully that will help you. I forget this formula all the time. I just think of it that way. It's way easier to remember. So let's see. So we know probability of A intersect B, or probability of B is 0.6. Now we create a new problem for ourselves. A intersect B. What the heck is that? So we can actually solve this because we know what A union B is. Now the formula for probability of A union B is equal to probability of A plus probability of B minus probability of A intersect B. And I'm going to show you why this is true as well. But what's nice about this formula is we have something we know, A union B. Actually, we know 3 of them, and there's 1 unknown. So we can eventually solve for this and be able to get this numerator. So let me show you why this is true first off. So A union B, let's draw another outcome space. So A union B is this whole area here. For events, let's just draw this is A and this is B. So how are we going to calculate A union B, the probability of A union B, that is? We're going to add this area to this area right here, plus this area. But the problem with this is that when we count this area, this overlap here gets counted twice. So what we're really calculating is not what we want. We want to get rid of one of those overlaps. So that's why we have this here. We're getting rid of that one overlap, A intersect B. So we're just left with this part, this part, and this part. So hopefully that clears up why this formula is true. So let's plug in what we know. A union B is 0.8. Probability of A is 0.6. Probability of B is 0.5. And this is what we don't know. We're trying to solve for. So from here, we can just do some algebra real quick. Let's see if you can see. Yeah, you can. Okay. And you're going to find that A intersect B, probability of A intersect B, that is simply equal to, let's see, 1.1. It's going to be 0.3. Okay. So now we know A intersect B. We can plug it directly into here. We can plug in probability of B. So let's do that. So A intersect B over there says 0.3. Of course, this we don't know yet, so I'll put that. And probability of B is 0.5. And we're asking, is that equal to 0.6? And you'll see that 0.3 divided by a half is 0.6. So we can confirm that this is true, which means that they are independent events. So not ME, but independent.
So we're going to start off with number 6 right here, which is basically saying that before we said that this was not the correct probability on how to calculate at least 1/6 in 4 dice rolls. And the reason why is because these are not mutually exclusive events. Rolling a 6 here, let's say the first roll, rolling the 6 here, doesn't mean that this is guaranteed to be a 6 or it's guaranteed not to be a 6. In fact, it means absolutely nothing for the next rolls. And what that means is that these events are independent of each other. And 2 events being independent means they have no bearing on each other in terms of their probabilities. So the probability of the first roll being a 6, that doesn't mean anything in terms of the second, third, or fourth roll being a 6. So we can use this fact that they're independent to calculate the correct probabilities in slightly different math. So to look at this first part, we discuss how it's incorrect. So what is the correct probability of getting at least 1? The tricky part of this question is the at least 1. Because what this implies is that means at least 1 means 1, 2, 3, or 4, right? So that would be 4 different probabilities we'd have to compute. We'd have to get the probability of 1 and the probability of 2 6s, the probability of 3 6s, and the probability of all 4 being 6s, and then combining those, which we don't want to do because four probabilities is a lot harder to calculate than 1, right? But there is a way to do this in just 1. And the key is the key is figuring out what is the opposite of at least 1. Well, I would say the opposite of at least 1, I'm gonna write that out, opposite, and that's going to be equal to, I'd say it's equivalent to none at all. So the opposite of at least 1/6 is going to be no 6s at all. So let me rewrite it actually. So no 6s at all. And that is something we can calculate. Pretty straightforward calculation here. So the probability of 0 6s. So let's say for just one dice roll. There's just one dice roll. There's 6 options. And only one of those is a 6. So there's 5 out of 6 left that are not 6s. So for one dice roll, that probability is going to be 5/6. But we don't care about one dice roll. We care about 4. So now let's generalize it to 2. Let's say 2 dice rolls. So we already said that earlier that these events are independent of each other. Dice roll 1 means nothing for dice roll 2. So since they're independent, we can use the multiplication rule and say for 2 dice rolls to have 0 6s, it would be 5 6 times 5 6. And we can do the same thing for 3 and the same thing for 4. So the probability of getting 0 dice rolls or 0 6s in 4 dice rolls, that probability is going to be equal to 5/6 to the fourth power, because we're just multiplying it by itself 4 different times. So we're doing 4 different dice rolls. And since they're independent, we can multiply those by each other. So this is the probability of getting no 6s at all. But that's not what the question's asking. The question wants at least 1 6. But since I already said that this is the opposite of at least 1 6, what we can do is we can say that this probability, the probability of at least one, probability of at least one, is going to be equal to 1 minus this opposite. So 1 minus p of 0. So we already established that that probability of 0 dice rolls is 5 6 to the 4. So that's going to be 1 minus 5 over 6 to the 4. And I think that, like, if this kind of question is on a quiz, that is definitely like a sufficient answer. But just for the sake of just this question, we can go ahead and calculate the actual probability of that. And that is going to be 5 6 to the 4th. And then 1 minus that. So that is around, what is that around? That is around 52%. So around 0.52. So you don't need to know that this is roughly 52. This answer right here on a quiz, this is good enough because we're not going to expect you to, do, I want to say complex math, but you're not going to need to simplify to the easiest possible answer. This should be good enough. And then now we can move on to the second part. Another game that I used to play was betting on rolling a pair of 6s at least once in 24 rolls of a pair of fair dice. And then he computed this probability the exact same way as up here, the exact same way of adding it a bunch of times to get a number. And that's incorrect. And this is incorrect for the same exact reason, that these are independent and not mutually exclusive. So we can use the same exact logic. So first we need to find the probability of 0 pairs of 6s. So the way we can do this, it's a little bit different, but same logic. So how many different rolls, how many different combinations of 2 dice rolls are there? This is the key to this question. So there's 6 faces on one, 6 faces on the other. You roll them independent of each other. So there are 36 different outcomes, right? So another important thing is, well, is it 36 or is it 36 times 2? Why is it 36 instead of 72? Well, the reason is it has to do with, how many permutations are there? Or does the order matter is a better way to say it. Does the order matter of the dice? Basically what I'm trying to say here is if you roll, let's say you roll 2 dice. Here are the 2 dice. So this is dice 1, this is dice 2. Let's say first die is a 2, second is a 3. Cool. Now, let's say we do the same thing again. And we roll a 3, and then a 2. This is dice 1, this is dice 2. Does this matter? Are these two different rolls? The answer is no. And in general, the answers are going to depend on the situation. In this situation, it doesn't matter which is dice 1 and which is dice 2. A 2 and a 3 is the same exact thing as a 3 and a 2. So because of that, there are 36 different options. If not, then there would be more, because you have to account for the differences in the permutations in the order, basically. You have to account for differences in order, but we don't have to do that here. So there are 36 possible dice rolls of a pair of 2 dice. So how many of these is a pair of 6s? This one's pretty easy. It's just 1. So there's only one outcome where it's a pair of 6s. Cool. So that means the probability. Let me rewrite this a little bit. 36 options. So the probability of 0 pairs of 6s is going to be the amount of non-pairs of 6s, which is 35, out of the total amount of outcomes, which is 36. And we are rolling this 24 times. So we're rolling these dice 24 times. So we're going to multiply it by itself 24 times because it's independent. So we can multiply by each other over and over and over again until we get our desired amount, which is 24. So that means probability of at least 1 is equal to 1 minus probability of 0. This is kind of a general thing that if you see like on a quiz or something, like if you see what's the probability of getting at least one thing, that should be a very big hint to think about it this way, where you want to subtract the probability of it not happening at all from 1. So same exact thing, 1 minus 35 over 36 to the 24. So again, that is a good enough answer for the quiz, but just for the sake of, just this video, we can calculate what that actually is. Okay. So this is roughly 0.49. And kind of, the reason I wanted to show that is because originally, the way he originally thought of it was to be his 2/3. And, they were betting money on this. So what that means is he thought originally that he was winning money most of the time. That if everything, completely normal, completely defined by chance, he would win this bet 2/3 of the time. When in actuality, he did his math wrong, and now he's actually losing money. He is losing more than he's winning. So this is just kind of, make sure you have your numbers right, basically. And this is how you would do these types of problems, is you have to check if they're mutually exclusive or independent. And if you figure out which one it is, you can kind of use that in your own probability computations, whether you add, multiply, both, whatever. However you need to do it, it's really good to define if they are mutually exclusive or independent or neither, and then use, whatever computations you're familiar with for those different types of probabilities to get the answer to the question. So again, this answer is just fine. It's probably, expected we're going to want to see. Or they're going to be, a little easier numbers to work with where you can actually compute it out just by hand in a very short amount of time. So yeah, this is how you are going to go about these types of probability problems. So remember, they're very key. I'm going to write it out again because I think it's important. At least 1, or probability of at least 1, is going to be equal to 1 minus probability of it not happening at all. Please remember this. This is very important. And yeah. So this is how you would do these types of probability problems.